Physics 2 review, second sem. Let's start with chapter 3, electric potential energy and electric potential. Electric potential energy, which is represented by the letter U, this is the energy a charged object has because of its position relative to the other charged objects. And what does it mean by this? It means if the two objects if the charged object is having a reference point which is a 0 point, it can create its own potential energy. And once it is closer to that reference point, the energy is lesser. But once it is farther from that reference point, then the energy is much bigger. Okay. Um, Electric potential energy is a scalar quantity. It means this is just talking about magnitude. It can be positive or negative depending on the signs of the charges, and it is using this formula U, which is the potential energy, equal to K times Q1 times Q2, which is the charge 1 and charge 2, and over R, with the distance between the two charges. And remember, you should know the value of K, which is the Coulomb constant, that is 8.99 times 10 to the 9. Okay, because this value is very important, especially if you are using this formula and some formulas related to this, because most of the time you'll be using K as your constant value. Okay, so this formula, when will only be applied when there are multiple charges. It could be two charges or more. Okay, but most of the time two charges, because we are only using two charges at a time. Once we're using this formula, we only have the Q1 and Q2 or any charges that you put in this formula. Now, the energy can be negative or positive, but remember, it is a scalar quantity. But why is it negative and positive? The negative and positive here is just our indicator if the two charges are attracting each other or pushing each other away. So if it is a negative energy, it means the two charges are attracting each other. Okay, so that's the indicator that we know that, oh, the two charges are attracting because it is a negative energy or potential energy. But if it is a positive potential energy, they are pushing away each other. And why? Why is it giving us a negative energy and a positive energy? It's because of their signs as well. So if Q1 and Q2 are both positive, if you multiply both positive, it gives you a positive answer. And everything will become positive as well. So that's why your potential energy is positive. The same thing for the two negative charges. So if you multiply negative and a negative, it gives you a positive answer. So everything will become positive. So your U is a positive energy or potential energy. But if you have a negative charge and a positive charge, if you multiply those two, then it gives you a negative answer, a negative product. The entire thing or the entire product here, if you multiply and divide everything, the answer will become negative. That's why your potential energy will also be a negative value. Okay. Okay. Now let's have an example for this setup or for this formula. If you have two charges and you put them away from each other, remember, we're not talking about reference point here. We're just talking about the distance between the two charges. Okay. So a while ago, I said that if you have a zero reference point and if the charge is closer to the zero reference point, the energy is lesser. But if it is farther from the reference point, the energy is bigger. Okay. So that reference point or distance can only be used later on in the uniform electric field. But here, since we have two charges and each charge, they have their own electric field which are not uniform, we will not be applying that thought yet. Okay, here we're going to apply the distance between the two charges. If the two charges are far away from each other, the electric potential energy is lesser. Okay, But if we shortened the distance between the two charges, the electric potential energy is greater. Okay, so why? It's because the relationship between the potential energy and the distance between two charges, they are inversely proportional to each other. And if we say inversely proportional, it means the shorter the distance, the greater the potential energy, U. And the farther the distance, the lesser the potential energy, U. Okay? So that's what it means by inversely proportional. They're going in the opposite direction. So once you make the distance shorter between the two charges, the electric potential energy becomes stronger. Just like a magnet, the force of attraction becomes stronger once you put them closer to each other, but once you put them away from each other, the force of attraction is now lesser. Okay, just like these charges, it's the same thing because forces and energy are connected or related to each other. Now, the second formula that we will be using for electric potential energy is this one, the one that I mentioned a while ago. So this formula can only be used if there are uniform electric field or parallel plates involved. Now, sometimes they don't put the parallel plates, the positive and negative plates. They will just put the arrows of the electric field. That is fine. Later on, I'm going to show you an example of that so that you'll not be confused what I meant by no plates. But there is an assumption that there are plates right there by just knowing that there is a uniform electric field. So it's not all the time that they will draw the plates, but they will always show you the electric field, the uniform electric field. If there is a uniform electric field, use this formula. Okay? And in uniform electric field, remember, as what I've said a while ago, electric potential energy is determined by the chosen reference point, where the potential is defined as 0, where it is located at the natural tendency of the charge. So, for example, if it is positive, its natural tendency is the negative plate. So the negative plate is it served as the 0 reference point or the 0 distance of our positive charge. But if it is a negative charge, the 0 distance is the positive plate. Okay, but most of the time we will be using the positive charge, so we're going to use the 0 distance as our negative plate. Okay, now aside from talking about electric field, there are times that electric potential energy, the energy, is connected to the electric potential, which is in volts. Okay, electric potential. So electric potential is closely related to electric potential energy. And if you multiply electric field and distance of the charge from its 0 reference point, that is actually electric potential. So in this way, we can change that E times D into V, and we can come up with this formula. And when can we use this formula? It is when you have potential energy and also electric potential all together in one problem. So if the two of them are present in one problem and there's no word stated as the uniform electric field, then you're gonna use this instead of this one. And electric potential energy is directly proportional to electric potential. Once the electric potential increases, electric potential energy also increases. Once the electric potential decreases, electric potential energy also decreases. Okay, so make sure to keep that in mind. Okay, so this is what I said a while ago. And the last one is the change in electric potential energy. So if there is this triangle symbol, it means there should be a final and minus the initial. So once we subtract the final energy minus the initial energy, it is equal to the negative of work. So it means whatever magnitude that you answer from subtracting the final energy and the the initial energy, you'll get the magnitude and just put negative to it, and that's already your work. Now let's answer this word problem. A positive 3.0 microcoulomb charge is placed between two parallel plates. So we have here the diagram with two parallel plates, positive and negative. that create a uniform electric field. So here it is now mentioning the uniform electric field. So we are now certain that we're going to use the second formula. The U is equal to E, which is the electric field, times the distance of the charge from its natural tendency times the Q. So U is equal to E times D times Q, because it shows us the quantity or the unit of the electric field here. So we're going to use that. And remember, the electric field here is shown 200.0 Newton per coulomb. So if you are not certain if it is an electric field, the unit of an electric field is Newton per coulomb. That's one of your indicators. Now, the charge is pulled or moved to the right at a distance of 80.0 centimeters from the positive plate. So, it means this charge here is a positive, and its natural tendency is in the negative plate. It means without pushing it, it will obviously be moving by itself to the negative, right? Because it has the natural tendency to move to the negative plate. So it means this negative plate is our zero reference point. Okay. Now, this charge here is moved 80 centimeters from the positive plate. So its initial position is here, attached to the positive plate, and it moved 80 centimeters going to the right. And we need to change that 80 centimeters to meters, because once we're using the distance in the formula, it should be in meters. Okay? So we can now solve for the energy for each position. So we have now two positions here. The first position, which is the time that it is attached to the positive plate, and the second position where it is now moved 0.8 meters away from the positive plate. So we have a initial and also a final potential energy, right? Because we have two positions, and those two positions, they have their own energy that they've created. Okay, so we're gonna use this formula. So we have a formula for the final. So this is the same formula. We did not change it. We just put F here for the energy, which is this is the final energy, the second position that it showed us, and the distance will also be the second distance that it showed us, and there is an initial energy as well, and the initial energy will also have its own distance that we're gonna use to solve it. Now, if the distance between the two plates are not given, and you are not certain of the distance of this first position to the natural tendency, which is this is the zero. Remember, we're not measuring the distance from the positive plate. We're measuring the distance of the two of them from the zero, which is the negative plate, because this is its natural tendency. So if the distance of the two plates are not given, we can assume, we can choose any number, any distance that we want, because in this question we are only concerning about the change. So whatever distance of the two plates that you choose, it will always give us the same change of the potential energy. It will not change. Okay, so you can choose any distance, but 1 meter is the most convenient one, so we can use the 1 meter apart of the two plates. So the two plates are 1 meter apart. It means the zero here, zero reference point, this initial position is 1 meter away from the zero, right? So it means this di here is 1 meter. We are now certain that this initial position or initial distance is 1 meter. How about the final position, which is this one, where our charge is now moved to the right? Of course, 1 meter minus this 0.8 meters, because we don't want this. We're only measuring from here going there, right? We're only measuring from here going to the zero. So this is the only distance that we're gonna measure. So what should we do? We just need to subtract the entire 1 meter by this one to get this distance, and that is 0.2 meters. Okay, so we already have this as 0.2, and this distance here is 1 meter, because attach itself to the positive, so it means it is 1 meter based on our assumption. And the distance F is 0.2 because we subtracted the 0.8 meters from the 1 meter. So we're gonna solve them, each one of them, and then subtract the 2 because we're looking for the change. Change means final minus initial. So solve each one of them. First, the final, we're gonna choose the distance 0.2, and the E, which is the electric field, it's the same. It's this one. And the charge is a positive 3.0 times 10 to the negative 6. Remember, micro means negative 6. And for the final, of course, we're gonna use the distance 1 meter because of the initial, because the initial is 1 meter away from the 0 reference point. So we're gonna use 1 meter for that distance. And the same values for E and Q because that's the same electric field, uniform electric field. It doesn't change. And the Q, it didn't change because it's one charge that we're using in this situation. So we're just using this same charge. So we just moved it from one position to another position. So let's solve these, and we have the answer after solving this. If you have this long answer, you can change this into scientific notation to make it look good. And this is now the scientific notation form of that answer. And remember, energy is in joules. The unit is in joules. Next, for the initial, so the answer is 0.006 joules, and make it in scientific notation. The answer is 6 times 10 to the negative 4 joules. And remember, you need to subtract them, the final minus the initial, and you'll have the answer of the change, negative 4.8 times 10 to the negative 4 joules. And since the change is negative, potential energy decreases. Okay, so always keep that in mind. That is also the things that you need to remember. If the change is negative, it means the potential energy is decreasing, because once this charge is moving closer to its natural tendency, potential energy is decreasing. But once this charge is moving away from its natural tendency, the potential energy is increasing because it's moving away from the 0 reference point. Okay. Okay. Next, what is the total potential energy? Crash it out. What is the total potential energy in this situation? This time, we're now involving multiple charges. Okay, not anymore the one with the electric field. So obviously, we're gonna use the one with multiple charges formula, which is this: energy, potential energy U, equal to the column constant K times Q1 times Q2 over R. Okay, so how do we do this? We have 3 charges, but we only have in our formula 2 charges involved, Q1 and Q2. Of course, you need to pair them up one at a time. Okay, that's the technique, because we're looking for the total potential energy. It means we're gonna gather the energies of each pair and add them up. That's it. That's how you get the total potential energy. So, for example, let's have, oh, by the way, the K, always keep in mind that is 8.99 times 10 to the 9. I will not give you the unit anymore, just for you not to be confused further. Okay, so we're gonna pair them up first. First, we're gonna label them. Let's just say this one is our A, this one is our B charge, and this one is our C charge. And let's pair them up one at a time. Okay, let's start with the pair of A and B. So we have the energy created by the 2 charges A and B. So we have multiply the charge QA and the QB and whatever distance between the two. So that's what we're gonna put there. And the pairing of B and C. So B and C and the distance between the B and C as well. So we're gonna get the energy created by B and C. And lastly, the distance, the energy created by A and C. And remember, the energy that you create for the A and C, the energy that you will create for A and C, it needs the distance between the two, and we don't have the distance here. So how do we solve this last energy if we don't have the distance? And That's the purpose of these other distances. This is now the application of geometry. You need to find the last side of the triangle by understanding that this is a right triangle. Okay, so it means the distance between A and C is the hypotenuse of the right triangle, and we're going to use the distance formula or the Pythagorean theorem, which is C squared is equal to A squared plus B squared. Okay, and you need to square it to find the hypotenuse afterwards. And if you apply that, of course, I don't want to go through with the process in doing the Pythagorean theorem. The answer here, after we solve, let's put their distances first for each one of them. And to figure out the distance of our AC, the distance using the Pythagorean theorem, we got 10 meters. So A and C are 10 meters away from each other. Again, we're gonna put that here in our R. And solving each one of them, put all the values here. We already know the value of K is this. The value of each Q are these. And don't forget that the micro means times 10 to the negative 6. So multiply them and divide by the distance. And we got the answer for the energy created by A and B, which is negative 1.2 times 10 to the negative 2 joules. And for the energy created by B and C, we have negative 6.7 times 10 to the negative 3 joules. And why are these two negatives? It's because A and B, we multiply positive and a negative. And for B and C, we multiply as well negative and positive. That's why the answer of their energies are negative. Now we have A and C. So we multiply positive and positive, filling out these values here, and we got the value of the energy between A and C as 1.1 times 10 to the negative 2 joules. It's a positive answer. Now, to get the total, you just need to add them up using algebra. The energy created by A and B plus the energy created by B and C plus the energy created by A and C, and that's it. After adding them up, the answer is negative 7.7 times 10 to the negative 3 joules. You can try it out using your calculator and you'll get the same answer as well. Okay, you just need to, don't forget to add the negatives. If there are negatives, you need to add the negatives if you're adding them up. Okay? Next, electric potential, which is the V. We mentioned this already a while ago. The V is related to the U, which is electric potential energy. And once the electric potential increases, the electric potential energy also increases. When the electric potential decreases, the electric potential energy is also decreasing. Now, electric potential is energy per unit charge. The unit is in volts. Since it's energy per unit charge, it means the energy U divided by Q. And remember, this formula, we've already used this a while ago. The U is equal to V times Q, right? The one that we changed the ED into V. So this is this. So we just manipulate the formula and we come up with V is equal to U over U over Q. Okay, so when potential energy and charge is involved, we're gonna use this. So if the two of them are mentioned, the electric potential and also potential energy, then the formula of this one is used, or this one. It's up to you if which one is being asked. So we're gonna use this one if the two of them, the electric potential, the energy as well, and also the charge are involved, then we're gonna use this. Now, if there is a charge involved and a point, a test charge, a point, reference point is involved, then we're gonna use this formula. So if there is a presence of charge and a distance of that charge from a test charge or a point, then we're gonna use this formula. Okay, so again, here this formula can only be used if there's no distance involved. Okay, there's no distance involved and there's no test charge, and if there is a presence of the electric potential energy, and the charge, then we're going to use this. But if we have a charge and a test charge or a reference point, then we're going to use this formula. because there is a distance between that charge and the test charge. So this will be the formula that we're going to use because of this distance r here. And last one, if it talks about uniform charge and we're looking for the potential, electric potential, then we're going to use this formula. Okay, we already used this a while ago, change the ED into V to form this, but we're going to go back here. So just for us to just talk about electric potential, so V is equal to electric field times the distance of the charge from its natural tendency 0. Okay, so of course there are plates, and sometimes the plates are not shown. I'm gonna show example of that later. Okay, now here, since it is now test charge and a charge, so like for example here we have two test charge A and test charge B. Electric potential, which is the V, is inversely proportional to distance because the r is in the denominator and the v is in the numerator. V is over 1. It's automatic over 1. So v is in the numerator, while on the other side r is in denominator. So they are inversely proportional. And what does it mean by that? If the test charge is moving farther from the charge, then the v is lesser. So the longer the distance, the lesser the electric potential. The closer the distance, the greater the electric potential. So they are inversely proportional with each other. So it shows here that which of the two has a greater electric potential. Obviously, the one that is closer to the test charge, okay, or the charge. So this test charge here is closer to this charge, then this test charge A has greater electric potential than test charge B. Both of them, they have their own electric potential, but test charge A has greater electric potential than test charge B because it has shorter distance. Okay, so the closer the test charge to the charge, the higher the electric potential. The farther the test charge to the charge, the lesser the electric potential. So keep that in mind. Okay, so let's change the diagram. This time from this simple diagram, let's make the diagram like this. So we now have two charges involved. The Q1, which is positive 2 microcoulombs, and the second charge, positive 1 microcoulomb. Now, don't be confused about this. We're just measuring the charges or the electric potential felt by each charge. Okay, so for example, let's focus ourselves to test charge A. So look at test charge A. Test charge A is creating an electric potential towards the charge Q1 because it has a distance 3 meters away from Q1. It means test charge A produce an electric potential from Q1. And since there is also a Q2 here, test charge A also creates electric potential from Q2. And whatever those electric potentials that it produce, you just need to add them up. So the electric potential that the test charge A towards Q1 plus the electric potential of test charge A towards Q2, add them up, and that is your total electric potential made by our test charge A. Okay, so test charge A will now be experiencing two different electric potential. The first electric potential it felt from Q1, and the second electric potential it felt from Q2. Okay, and of course you need to solve that here. The test charge felt by Q1, by test charge A from Q1, solve that, and the electric potential felt by test charge A towards Q2, you need to solve that, and once you're done solving them, add them up, and that's the answer for the electric potential of the A. Okay, since there are now two charges, so you need to actually do that for you to get the actual total electric potential of test charge A. And for test charge B is the same thing as well, because there are now a presence of two charges. So test charge B will also be having an electric potential towards Q2 and also an electric potential towards Q1. So you're going to form this formula as well. So an electric potential created towards Q1 and an electric potential created towards Q2. Okay, and of course, we're gonna simplify these, put the distance of Q1 from test charge A, which is 3 meters. This is the one that we're certain of. It's 3 meters. But we are not sure of this distance here, the distance towards Q2. And how do we get that? Of course, we're going to use the Pythagorean theorem. So Pythagorean theorem, we can get the value of this distance of Q2 from QA, discharge A, and by using the Pythagorean theorem, 3 squared plus 4 squared, add them up and then square root, and you get 5 meters for this distance. So R here is now 5. Okay, and we can now solve that by plugging in all the values in these variables, and we can get the answer. For the B, we are certain of the 1.5 meters away from Q2, so that's why we have the R here, 1.5 away from Q2, but we are not certain of the distance away from Q1. So we're looking for this distance here. And again, we're going to use the same method, Pythagorean theorem, to find this distance. 1.5 squared plus 4 squared, add them up, and then square root. The answer is, that is 4.27 meters. And we're going to put that in our R towards Q1. Now, let's gonna solve the electric potential for each test charge. So let's start with the A. Of course, if we put all the numbers here, the value of K and the value of Q1 and Q2, if we perform all the solutions, we can get the answer as 7,791 volts. And this is already a round off answer. And for the electric potential created by test point charge B, we need to just plug in all the values again and do the solution, and after calculation we got the answer 10,204 volts. This is rounded off already. If we have all these, we can now compare them, which one has a larger electric potential and which one has the smaller electric potential. So obviously the one that is closer to the charges has the larger electric potential. And which of the two charges are closer? Of course, test charge B. Look at test charge B. Here, test charge B is closer to Q2, although it's farther from Q1, but it's closer to Q2. And test charge A is closer to Q1, but it's farther from Q2. And their distances really creates like a different value, but it doesn't matter as long as we've come up with the sum of all the electric potential for each charge, then that is already the total electric potential received by the two charges. And in here, test charge B receives the higher electric potential. And also this one. This time, we are no longer involved the test charge into a charge. This time we're involved with the uniform electric field. So if there is a uniform electric field, remember the formula that you're going to use, especially if we're talking about electric potential, it should be V, and the factors that you'll be using are the electric potential, electric field, and the distance of the charges. Now, let's look at this charges here. These are test charges, okay? So most of the test charges are positive. Okay, always keep that in mind. And since they are positive, its natural tendency is the negative plate, right? So the negative plate is their zero reference point, or the 0 meter distance. The farther from the natural tendency, the higher the energy. It means that farther they are from the 0 reference point, which is their natural tendency, the higher the energy. And remember, the higher the energy, the higher the electric potential as well. So since electric energy, potential energy and electric potential, they are directly proportional with each other. or to each other. So higher electric potential energy, higher electric potential as well. So the farther they are, they have higher energy, and higher energy means higher electric potential. So since A is farther from its natural tendency, which is negative, A has a larger electric potential energy, larger energy, U, and it has also higher electric potential. Because it has larger electric potential energy, it should also have a higher electric potential, V. Okay, and B and D, they're the second highest. So A has the highest energy because it's the farthest from the natural tendency, or the zero distance, or the zero reference point. Test charge B and D are the second highest, and they have the same energy, electric potential energy, and both of them must have also the same electric potential. Only yes, it's true, since we're talking about test charges, but if we're talking about charge, the normal charge, charges could be a different value, but here, since we're talking about test charges, then they should have the same electric potential if they are in the same line, or the same position, or the same distance from the plate. And obviously C is the closest to the natural tendency, or the zero distance, then it has the lowest energy. And if it has the lowest energy, it will also have the lowest electric potential V. Okay? Now, this is what I meant. There are times that they will not show you the plate, but they will show you the electric field. These lines are what we call as electric field. Now, this is tricky because this time you don't know where is there the natural tendency of these the test charges. You need to keep in mind that the positive plate will always be the where the arrow's coming from, and the arrowhead of the arrows is always pointing to the negative plate. So that's the natural tendency point where the arrowheads are, because the arrowheads is always pointing to the negative plate. Although the negative plate is not there, they are going towards the negative plate. Okay, so always keep that in mind. Even though there are no plates, it is always it is giving us the idea that there is a negative plate here, because the arrows are going that way. The arrows of the electric field is always going towards the negative plate, and the positive plate is always the tail of the arrow of the electric field. Okay, always keep that in mind, and it won't change. The test charge A is the highest energy because it's the farthest from the arrowheads, which where our negative plate located, and the test charge B are the second highest, and they have the same electric potential because they have the same distance from the negative plate that is now invisible here. And the test charge C is still the lowest electric potential because it has the lowest energy, and it's closer to the zero reference point, or the natural tendency, the negative plate. Okay, so I hope that you will not be tricked with that. Okay, and another thing. So if two objects, charge objects, are if they are there are presence of two charges, two objects with charge, there is always an electric field created. Okay, all the time. Even though you put them too far from each other, they will always create an electric field between them. Just like this one. We have two objects, negative 10 volts. It means that's the electric potential created by that object. And the second object has an electric potential, 5 volts. These two can create an electric field between them. Okay, so if you are already certain about their electric potential, there is already a given voltage or volts for each one of them. It means they have their own electric potential. So if they have their own electric potential, they should create an electric field all the time. Okay, and how much is that electric field? Now, the formula, if we're talking about electric field and electric potential, is this one or this one. This is the formula if there is an electric field created. All you need to do, if you are finding for the value of the electric field, we're finding for E, we need to put the E on one side, isolate the E, and put the other variables on the other side, and it forms like this: V over D. So we divide D both sides, and D will now be at the bottom. So it's electric field equal to the electric potential divided by the distance. Okay, so make sure not to forget that. Now, since there are two of them, there are two electric potentials involved, we're gonna put them into an absolute value. And we're gonna assign which one should be our final and which one should be our initial. It doesn't matter. You can just choose the left side is the final and the right side is the initial, as long as if you already choose the left side is the initial, all throughout whatever other examples, you should always choose the left side as your final and the right side as your initial. Okay, so it won't change anymore. So like for example, I'm gonna choose my left side as my final and my right side as my initial. And the same thing for other objects. Like for example, if there are plates and they are given with the different volts, you're gonna do the same thing. Let's solve for the electric field created by these boxes first. So assume that the distance, since we have D and we are not given with the value of the distance, just these, we can actually assume a 1 meter distance. Okay, remember, assumption of the distance can only happen if it is a change, if you minus a final and an initial. So assumption can happen. So we have our final is -10, we put -10, and our initial is +5. Again, I choose the left side as my final and right side as my initial. So I'm gonna do the same thing for all other examples all throughout. So here, my distance is 1. So solve -10 minus 5, that gives us -15, and since there's an absolute symbol, that becomes 15, +15, divided by 1. So our electric field here felt by these two, made by these two boxes, it's 15 Newton per coulomb. So that's the electric field. Now how about the electric field created by these two plates? So we have the same process. We're gonna choose the left side as our final and the right side as our initial. It doesn't matter, the answer will always be the same as long as you're consistent. The left side should be your final and the right side should be your initial. Okay, so our right side is our final, so -4. Our left side, our left side is the final, right side is the initial. So be careful with this. Sorry. Since the initial is -10, don't change the minus yet, okay? Minus, and then put the -10. Unless if you're already certain that you can combine the minus and the negative, and that's it. So obviously in mathematics, the minus and the negative becomes positive, okay? They will now be added. So -4 plus +10, that gives us +6, okay? And over 1. So it means the electric field created in between these two plates is +6 Newton per coulomb. And that's it for chapter